And I now welcome Robin Grimes, Professor of Materials Physics at Imperial College and a Specialist Advisor to the House of Lords review of nuclear research requirements for the UK. It is, of course, which I only learned this morning, the 33rd anniversary of the accident at 3 Mile Island. How appropriate.
Thank you for that.
So, I was going to lead on Fukushima, but, basically you are saying that despite the concerns about accidents, about terrorism proliferation issues, and even capital costs, we do have the chance to see another nuclear renaissance, which could provide us with, you say, 1,000 years of energy.
Yes, that's right. And I think in common with the last speaker, it really all comes down to the question of cost. So I'm going to start off with a blindingly obvious comment, which I think is clear from what you've just mentioned, that nuclear energy is controversial. I think that's probably one thing that we can all agree on pretty much immediately. I've actually put a couple of quotes up there, a typically sort of pro-type quote and a typically kind of anti-like quote. And I suspect, in common with many people in the audience, I could probably argue both pro and anti on both of those sorts of issues. And I think it's also true that we could probably agree with the statement down here as well, that in general we can think of new reactors being built in the UK going forward, but we are very reluctant to differing extents to accepting those nuclear reactors relatively close to us. And it's a very interesting sort of debate, and again we could talk all night about just that issue, I suspect. But essentially, the public understands, or doesn't understand, the complex issues associated with running a nuclear reactor. And of course, that's understandable. But I think the public has a very strong sense of the risk. So it's one of the really crucial things to try and have people understand is what happens in a reactor, how does it work. And so I think I'm going to turn this reactor on for a moment. There you go. And what I'm pointing out here is something relatively straightforward, and that's the nuclear reactor. That's where the reactions occur. And this is a PWR reactor, and it's really the sort of reactor if we go for a new build in the UK, it's the kind of reactor that we would be building. And you can see it's exchanging the energy created in the nuclear reactor here to produce steam in the generator, which turns the turbine and so forth to create the electricity. All of this part is pretty common whether or not you are creating the heat through a nuclear reaction, through coal, through gas, even through oil. Now, why is it, if it's so controversial, why is it, if it's so challenging, that we're really interested in it? And it really comes down to something quite simple. So I'm afraid we're going to have to do a bit of physics. First of all, you have to remember of this nuclear reaction that what happens is there's a tremendous amount of energy liberated, and that goes into the nuclear fuel, it disrupts the nuclear fuel, and it creates heat. And it actually creates an incredible amount of heat. One of these nuclear reactions, this fission event, releases 200 million units of electricity. If we compare that to the situation for a chemical reaction, it liberates 1 unit of electricity. So here's my other very obvious, blatantly obvious statement. Nuclear fuel is an incredibly compact energy source. And that's really what is so attractive about it from an engineering energy point of view. Now, uranium is certainly a limited resource. Actually, it's not particularly scarce at the moment, but eventually we are going to have to use it more efficiently. At the moment, the way we use nuclear fuel, we only use about 2 or 3% of those uranium atoms in the nuclear fuel. 2 or 3%. That really is an astoundingly small amount. So we're going to have to learn to use it more efficiently if it's going to be a sustainable process. Now actually, we've been producing nuclear electricity for a long time. So here in this little black and white photograph are 4 200-watt bulbs, and they were turned on the 20th of December 1951 at the first reactor to produce electricity, which was EBR-1, Experimental Breeder Reactor number 1. So immediately, something interesting. It was a fast breeder reactor. It wasn't a conventional PWR-like reactor. The first reactor to produce electricity was a breeder reactor. By 1957, grid electricity was being supplied in the UK, the USSR, and the US. By the way, this is a picture of that first reactor's house, just here. And as you can see, they were obviously not too sure about the technology because it really, truly is in the middle of absolutely nowhere. I have been, and boy, is it a long way from anywhere. And there you go. But anyway, it was a fast neutron spectrum. So that was a sort of a generation 1 type of reactor. In the UK, we had these Magnox reactors. And indeed, we still have one of those Magnox reactors running until 2 weeks ago. We had 2 running. Following that, we followed an advanced gas core reactor route, which was very unique to the UK. And most of the rest of the world followed light water reactors, and as I said, particularly a PWR, pressurized water reactor. And Sizewell B in the UK is an example of a pressurized water reactor. In fact, it was the last one in the West to be connected to the grid. So we have the most modern PWR reactor in the West, actually, in the UK. That's the kind of reactor that, as again, if we go in for new build, it's the sort of thing that we will be building. The AP1000 and the EPR are examples of modern designs of those PWR-type technologies. Now, this is what I've been charged to talk about to you this evening. This is the so-called Generation 4 reactors. And the sort of question is, what does a Generation 4 reactor, what sort of design is it? And actually, it's not one design. And in some ways, I don't think it's a very good way of thinking about it, because it's a series of different types of designs, all of which are supposed to be all these wonderful things stated here at the end, which you can always state when you've not actually built something. Call me a cynic. Nevertheless, you can see the sort of timelines when these sorts of technologies were thought about according to this particular DOE document here. But many of those designs, as you're going to see, are really evolutions on existing designs, going right back to EBR1. So let's have a little bit of a think as to why we're even thinking about such radically different sorts of designs, different to our PWR. And it goes back to, again, to this use of uranium. At the moment, most reactors use this open, once-through type of fuel cycle. The fuel goes in, it comes out, you then have to dispose of it. And again, 2 or 3% of the uranium is used. In the UK, we have been able to take out some of the uranium and the plutonium that's produced with a view of perhaps putting it back in as mixed oxide fuel. We never quite got round to that. And as a consequence, having gone part of the way through, we've ended up with an awful lot of this material, and the government's just taken a decision that we'll probably be using it in these new reactors if we build them. The alternative, finally, we could fully close the fuel cycle by using fast reactors in particular. And in that case, we could use up to sort of 70, 80%. So this is a 20 to 30 times increase in the efficiency of the use of the uranium. This also has the added advantage here that if you remove the plutonium, uranium, and the so-called minor actinides, that's other elements around uranium, plutonium, then the nuclear waste left over after 300 years has returned to its relative radiotoxicity of the mine from which it was taken in the first place. If you do what we've done in the UK, this sort of partial recycling, you can get to 9,000. It's kind of the pyramids, so we have built structures like that. Maybe Stonehenge, but I'm not a historian. If you just do the once-through cycle, then you don't get back to where you began for 300,000 years, which is a series of glacial periods, by the way. So why on earth are we not doing that? And it's very simple. It's the cost. But if we were to do that, if we, again, are able to spend that money, then, and again, excuse me, I realize there are lots of numbers here that we could argue about all night. There's the once-through for uranium. But if we were to use it in a fast breeder reactor, we increase the use. And if we then include elements like thorium in a fuel cycle, then we have something up to 2,000 years worth of fuel at our disposal. Why don't we do that? Again, of course, how much are you willing to spend? Those are the 6 types of Gen 4 type reactors, and I'm going to just mention one thing: closed fuel cycle, closed fuel cycle, closed fuel cycle, closed fuel cycle, and then these last 2, which would be used in tandem with some of these other designs to perhaps close the fuel cycle. They're trying to do quite different things. I wish I had so much more time to explain this to you, which I don't.
You don't?
Okay, thank you. But different reactors in different places for different jobs. One of the reasons I don't like the idea of putting them all into this Gen 4 concept is that there are also small modular reactors which offer greater flexibility for grid capacity, limited risk capacity environments, for example. And I think those may well be built alongside. One of the other interesting things is they all have these marvellous names. My favourite here is the Toshiba 4S, for super safe, small and simple. There you go. Marvellous. So my final slide, how will Gen 4 aid in a nuclear power renaissance? How could it aid us? And I think it really comes down at the end to this simple bullet point. The Gen 4 attempts to address key issues of fuel sustainability, passive safety, proliferation risk, and offering flexibility to develop passive systems that can develop hydrogen or could develop electricity for other chemistry, as well as closing the fuel cycle and allowing us to use the uranium atoms as we perhaps ought to have.
I'm sure the audience will have lots of questions about these points, these promises by the Gen 4. Maybe just one quick question. I mean, if we define our aim to be to pretty much eliminate CO2 emissions by mid-century, and this becomes commercially viable in 2030 and then takes 10, 20 years to build, this won't be part of the solution. It comes too late, doesn't it?
That is an issue. I mean, it really is an issue. And you know, one of the things that I didn't emphasize here is that, you know, there's an awful lot of work that needs to be done on these types of reactor systems before they really become commercially viable, except that if we think about, for example, the sodium-cooled fast reactor, India will have a sodium-cooled fast reactor which will go online next year. So the different Gen 4 designs will become available to us at different times and can make a contribution, in fact.
Right, questions. Start in the front and then, sorry, I will go to the back right after. Keep it really short because we are already beginning to run over.
Okay, thank you. Craig Bennett, Director of Policy and Campaigns at Friends of the Earth. And Robin, thanks so much for that. I'll start off by just saying, you know, really support the research into this. Who knows where we're going to be in the second half of this century?
Absolutely.
So no problem with that. But I would say, because of these timescales, you know, this is completely irrelevant to making any difference to climate change, and therefore, I would argue, is not a game changer in this debate. That's even just from a kind of technical point of view of the development of this. But then you add on the kind of social and economic things. You know, the nuclear industry has had a whole history of over-promising and under-delivering. What nuclear power station has come in under budget and delivered sooner than it was supposed to. And we've seen that problem time and again. Let's not forget that Margaret Thatcher, when she came into office, promised to build 10 nuclear reactors, and in 15 years she built just one. And she was a pretty determined lady. So, you know, there's a real problem there. And I think actually the biggest risk about nuclear power these days is that we bank on it to help us solve climate change, and then it doesn't deliver, and we end up with coal and gas, and we don't deal with climate change. That is surely the biggest problem. And my real concern, which I'd love to hear your thoughts on, doesn't this all just deflect attention, political will, engineering capacity, and, of course, investment from the vast number of other proven options that will deliver at scale, quicker and cheaper? Let's not forget that the cost of solar PV, for example, has fallen 30%. 30% in the last year. So that's
right. Does it divert attention from renewable energy?
Gosh, well, we need a couple of hours on some of those. I mean, numbers of the points that you make, I think, are very valid, as a matter of fact. I mean, I'm not a hurrah nuclear energy type advocate at all. You know, I think you have to be realistic. All big-scale engineering facilities have problems. All of them have failed to deliver at certain times. The issue of learning how to build nuclear reactors has indeed been a problem. And if you just look at the problems in Finland at the moment with the Riva reactor. Conversely, you can look at the Korean situation, which over a period of time, with an energy policy dictated by a government with a will to have an energy policy, delivers nuclear reactors on time and under budget. Only at the end. At the beginning they had difficulties, but by the end they worked out how to do it. It is possible to do it. It's the same, my comment about the India situation. There is a distinct will. I think the government needs to have and make a decision about a clear energy agenda for the UK so that people can make those sorts of investments. My worry, actually, is as to whether, you know, actually getting the money to build the reactors in the first place. I think that will be the reason that we actually don't build nuclear reactors in the UK. I think the other things we'll overcome.
Yeah, which brings us back to the whole issue of pricing carbon. But let me have 2 ladies, please, because we haven't had any ladies. Lady number 1, and then followed by another lady. There we go. Cluster those 2 questions.
Thank you. I'm not sure I approve of being picked just because I'm a lady, but thank you anyway. I'm Beth Taylor. I'm from the Institute of Physics, but I used to work for the UKAEA and was involved in cleaning up at Dounreay. And I'm just a wee bit worried about history repeating itself, in the sense that Dounreay did produce 2 fast reactors which worked.
They did.
But by the time they were working, the whole problem about, there's going to be a huge demand for uranium and everything's going to get terribly expensive and fast reactors will be worthwhile, had evaporated because no big nuclear program had happened, there was no huge demand for uranium, and so sadly the whole experiment was actually a commercial failure.
It was a commercial failure, yes,
and I'll just
absolutely.
finish, I'll be really quick. Plus the fact that you were closing the cycle with reprocessing and dealing with some rather nasty chemicals, including liquid sodium coolant, created a real clean-up problem. So I'm just worried about getting back into the same cycle.
No, absolutely.
Let's just get the second question and then address both in like 2 minutes.
I'll try and remember the first. Just to prompt me if you know.
Hi, my name is Maria Carvalho from the Grantham Research Institute on Climate Change and Environment. And my question has to actually talk about the carbon intensity of the entire supply chain of nuclear power. So if you were to look at uranium mining to the processing to using, and also storing it for the transport and storing, and the energy intensity of those processes along with the carbon intensity, can we really claim that nuclear power is carbon-free?
Oh, I don't claim for a moment that nuclear energy is carbon-free. Not at all. I claim it's low carbon, but it's certainly not carbon-free, for all the reasons that you've just said. And one of the problems is that there are many different sets of numbers, and I'm not an expert in that particular area, which put nuclear energy slightly more or slightly less than onshore, offshore wind, and so forth. So I think there's an awful lot of arguments, and I would like to see more work specifically in that area. So I think, I sort of agree with you by saying that I don't, as it were. So that's the first thing, because I know we're running out of time. The second thing, yes, absolutely. So there were 2 things a number of things that I didn't go through. First of all, I actually don't think we will be building Gen 4 reactors in the UK anytime soon. I think what's going to really concentrate our minds is life extension for AGR plant, dealing with the graphite problems and so forth, which I think you'll be probably familiar with as well. I think we will then build increasingly evolutionarily better PWR, conventional PWRs. We might find ways of recycling, multi-recycle MOX. We've got an awful lot of civil plutonium that we need to deal with. The government's indicated that. And so I think the UK might actually come to this a little bit later than some other countries do. I see that the shift in nuclear enterprise has moved to Southeast Asia very, very strongly. And I think we'll see quite a lot of the developments in Gen 4 there. But I was tasked with talking about Gen 4 tonight, so that's what I had to do.
Well, thanks, Robin, and sorry to cut it short yet again. It does feel like a bit of an impossible race through these issues. Thank you. And